And today, let us look into heat equation. Heat equation. Heat equation. Okay. When it comes to heat, there are certain thermal properties that you are supposed to know before going for heat equation. Okay. Every material, suppose I take this material, every material has certain thermal properties. Okay. Now we'll assume that this material that we consider is all about a homogeneous material where the thermal properties at any point inside this material is same. Okay. Thermal properties means what? There are certain properties like diffusivity properties and then thermal diffusivity and then heat capacities of a material. Heat capacity of a material means the amount of heat that it can retain. Different materials will have, based on their properties, it will have different heat capacities. Suppose in a given material at certain point heat capacity is more and certain other point heat capacity is less, suppose, then there will not be homogeneity inside the body. Okay. So we assume that the thermal properties are same, the diffusivity properties are same, as well as your heat capacities are also same inside a thermal material, Okay. Now, given any material, suppose this is room temperature, and we always assume that room temperature is at 0 degrees. When I mention room temperature, I don't expect room temperature is 22 degrees or 23 degrees centigrade. No. We assume, theoretically, we assume room temperature is at 0 degrees. Okay. Suppose there is an object which is outside the room, okay. Based on the outside temperature, it might be having certain temperature distribution inside already. Certain temperature distribution inside this material already that exists because it is outside. It might so happen that there exists some kind of temperature distribution inside. Okay, it might be 0 here, or 0 here, 100 here, 20 here, 80 here, whatever. Some kind of f of x temperature distribution is there. At a given x, suppose x is 0 to x equal to L. Okay. At x equal to 0, some temperature distribution, x equal to 1, some temperature distribution, x equal to 2, 3, 4, 5, 6 up to L. There are certain temperature distributions inside. Okay. That means when the body comes to the experimental room, the room, suppose assume it to be the experimental room, it already has got some temperature distribution inside it. Okay. That's what we call it as initial temperature distribution at T equal to 0. T equal to 0, initial temperature distribution. Now, what happens when the body is inside of a room? This has got a higher temperature when compared to, might be different distribution, but relatively it has got higher temperature when compared to its surroundings. So since there is difference in temperature, slowly this body loses heat to the surroundings, and slowly it tends to decrease its temperature over a period of time and finally becomes room temperature. Right? Finally it becomes room temperature distribution inside the body. That's what it's going to happen. Okay. Now, in what rate that the loss of heat would be there is something we have Newton's law of cooling and all those stuff. There are different properties there, different phenomena are there. Whatever the phenomena are, one thing that always happens is when you have a body at higher temperature, then it is the tendency of any material is to lose heat to surroundings. By the way, its temperature also gets reduced. The temperature gets reduced and it loses heat also, right? That property is always called as transient property. transient property of a material is that any given material, the thermal property of a material is to lose heat and decrease its temperature to finally room temperature. Okay. Now, there is one more property called as steady state. Steady state. What is the steady state? If after some time means how much time it takes for this material to come to room temperature? Ideally, it takes T, time goes to infinity. Time goes to infinity because if suppose this is at 100 degrees, this is at 0 degrees, the difference is so high that rate of exchange of heat will also be very high. If the difference comes to, suppose it comes to 90 and 0, the difference is little bit small. Therefore, the rate of exchange of heat comes down. And still suppose this got to 20 degrees and surrounding is 0 degrees. Difference is very small. Still the rate of exchange of heat comes down. So as the difference comes down, rate of exchange of heat also comes down. And ideally, as T goes to infinity, this becomes steady state. Are you getting that? This comes to steady state. As T goes to infinity, this transient property also has to be satisfied till the time T goes to infinity. At the same time, once T goes to infinity, steady state should prevail. Are you getting what I am saying? Once T goes to infinity, the steady state should prevail. So overall, both of them will be working in your equation. So suppose if I say transient property is UT and steady state property is US, your distribution of temperature U of x comma T will always be U steady state plus U transient state. As T goes to infinity, UT becomes 0. So finally it lands up at US only, steady state temperature distribution only. Are you getting that? So any temperature distribution, any heat equation, whenever you are trying to solve, it always will have two things. One is steady state temperature distribution plus the other is transient temperature distribution. Both of them should be there. Are you getting that? Do you understand these two? Transient as well as steady state. Getting that? So assuming that there is some point at which T is not infinity, but still US still exists. And US does not depend upon time actually. US does not depend upon time. This plus this will always be there. Okay? Fine. Now, so what is this equation? Equation is dou square U by dou x square equal to 1 by C square dou U by dou T. So how many conditions are required here? Okay. How many conditions are required? 2 conditions on x and 1 condition on T. Okay. 3 conditions are required. So any given object, generally since we are looking at one dimension heat flow, so heat flow will be only along x direction. Suppose this is A, this is B. Suppose this is x equal to 0, this is x equal to L. X equal to 0 and x equal to L. Suppose this is maintained at 0 degrees, suppose this is maintained at 100 degrees from now onwards at T equal to 0. Then U of 0 comma T will be equal to 0 degrees. U of L comma T will be equal to 100 degrees. Is it or not? And when this rod is kept here, it always might be having some kind of temperature distribution inside it. At time T equal to 0, U of x comma 0, some kind of f of x temperature distribution would be there. The meaning of this is, a rod is there something outside which has already got some temperature distribution f of x at time T equal to 0. Suddenly it is brought inside and at different temperatures would be maintained at both the ends. Here I will maintain 0 degrees from now on, from T equal to 0 onwards, this is maintained at 0. From t equal to 0 seconds onwards, this is maintained at 100. Already there might be some temperature distribution inside, but from now onwards, I will maintain 0 here, 100 here. Till the end, I am going to maintain 0 and 100. So, since there already exists some temperature distribution that will be redistributed to suit to 0 here, 100 here. Are you getting? To suit to 0 here, 100 here, and as t goes to infinity, finally the temperature redistribution inside will also come to steady state, which maintains 0 here and 100 there. Are you getting? This is the one which we are going to solve. Okay. Sometimes some kind of heat flux will also be supplied here. Heat flux we try to supply from one of the ends. Sometimes we insulate this end. Insulation can also be done. There are different scenarios altogether. Okay. So each scenario we try to solve now. Now we'll go with the first scenario. Both ends, first scenario. Type 1. Both ends maintained at 0 degrees centigrade. Both ends maintained at 0 degrees. Okay. There is some already temperature distribution inside f of x, but now onwards I will maintain 0 here, 0 here. Okay. So it quite obviously it means u of the conditions would be u of 0 comma t is 0, u of L comma t also is 0. These two we call them as boundary conditions, and one initial condition is there, u of x comma 0, which is equal to f of x, which we call it as initial condition. Okay. Let me write these conditions here so that it does not disturb our flow. U of 0 comma t equal to 0, u of L comma t also equal to 0, u of x comma 0 equal to f of x. See, not necessarily every time should be 0 and 0. It's a very simple case being 0 and 0. Okay. Let this be equation number 1. Let the solution of 1 be u of x comma t equal to capital X, which is a function of x alone, into capital T, which is a function of time alone. Now, any vague imagination now, any vague imagination of what might be the steady state? Some temperature distribution, some heat is there inside, some temperature distribution inside, which is f of x. Okay. Now suddenly I started maintaining 0, 0. Slowly what happens as time passes, redistribution happens to come to 0 and 0 here. Is it or not? To come to 0 and 0 here means that everywhere finally once the heat is lost completely as t goes to infinity, as time goes to infinity, heat is slowly lost, finally it comes to steady state, which would be 0 steady state everywhere. Everywhere it has to be 0. A flat straight line will come. A flat line temperature distribution, which is a steady state temperature distribution, has to happen, right? Okay. We'll see case by case. Okay. Anyway, substituting in 1. In 1, we get what we get x double dash into t. What is c here? C, you take it as diffusivity constant. where C is diffusivity constant. Sometimes people refer to as K also. K. I have taken C square instead of C or K because computations become easy. That's the only thing. Or else somewhere or other we have to take root K. Why unnecessarily root K has to be taken? We'll take K. Okay. So that this also implies x double dash by x is equal to 1 by C square T dash by T, let it be equal to K. Let it be equal to K. Case 1. What will you take? K equal to 0. Okay, Naidi? Right? Same thing like yesterday's. K equal to 0. This implies x double dash equal to 0 and T dash also equal to 0, which implies x equal to ax plus b and capital T equal to C, where a, b, c are arbitrary constants. This implies u of x comma t equal to ax plus b into c, which is dx plus e, where ac equal to d, bc equal to e. Now apply the conditions. U of 0 comma t is equal to 0. This is equal to e. X is 0 means e. U of L comma t equal to 0. L comma t means d into L. L is non-zero, therefore d has to be 0. D equal to 0. This implies u of x comma t equal to 0. What is this? What? Cannot be accepted as a solution of a heat equation, but wrong. This is called as zero steady state. The steady state that I am talking about, remember the steady state I am talking about, which will happen as t goes to infinity, is this one actually, because it is ax plus b variety, y equal to mx plus c, the straight line. Since the final steady state that is going to happen finally will be a flat line, 0 and 0, therefore it would be a zero steady state, which is this one. Case 1, when k equal to 0, always gives you the steady state temperature distribution which is going to happen finally, which in fact is my US. US, this is going to be my US, which is a steady state temperature distribution. Yesterday when I was discussing, if you remember, I was telling one point. Case 1, k equal to 0 might be invalid in the case of wave equation, but not necessary every time. Case 1 also can be a valid case, especially when it comes to heat equation. Case 1 is a valid case which actually gives us the steady state temperature distribution inside. That is steady state temperature distribution inside the rod. Okay? So don't say that it's invalid. Most of the Indian author textbooks say it as invalid. It's not true. Okay? Most of the Indian author textbooks say that k equal to 0 in this case, whenever 0, 0 is there, they say it invalid, but it's not invalid. It actually represents steady state temperature distribution. That's it. Transient state it does not reflect. Because transient state, what we need to have, the basic concept of transient state itself tells us that as T increases, temperature should decrease. Right? As T increases, temperature should decrease. That phenomena should appear in your transient state. Right? As T goes to infinity, temperature should become 0 finally. Okay? That's what should happen in the transient state, which of course transient state is not reflected here, but this actually is the steady state. Is the steady state temperature distribution and remember always one thing, the steady state temperature distribution always depends on boundary conditions only. Is it or not? Here some temperature, here some temperature, that's it. Steady state is least bothered about what happens during the course of time. It's only bothered about what is the temperature here, because we are always talking about homogeneous properties inside the body, right? When the homogeneous material is there, steady state only depends on boundary condition. It does not depend on time conditions. Okay? Suppose if I maintain 20 here and 60 here, the length of the rod is 100 centimeters suppose. Okay? At the steady state, what it should happen? 20 here, 60 here. Since it's a homogeneous body, I should have a straight line which represents something y equal to mx plus c. Okay? So it should be something like us of x I will get, which would be 20 plus 40x. 4x. 4 10 centimeters పెట్టుకుందాం అది బెటర్ 20 plus 4x సరిపోయిందా 20 plus 4x x equal to 0 20 x equal to 10 40 plus 20 this y equal to mx plus c. So this straight line should look like 20 plus 4x finally. If at all this is 20 plus 60 is the scenario that I have in the boundary conditions, then the k equal to 0 case would have given me 20 plus 4x. The D and E values I would be getting it as 4 and 20. We'll see this scenario later on. But I just want you guys to understand that k equal to 0 is not an invalid case. It is completely a valid case which actually gives us steady state temperature distribution inside the rod. Is this clear? Okay. F of x 0 కాదు ఎక్కడ t0 దగ్గర ఏది this u does not depend on time irrespective of time. Okay, this in fact is just not u of x comma t, this is u of x only. T సంబంధం లేదు irrespective of time. Irrespective of time is it? Irrespective of time, the steady state is this one. This is only us. But what is your u of x comma t? It is us plus ut. Ut కూడా వస్తుంది ఇంకా. This is 0, but you are going to have ut also, which actually depends on x, which also depends on time also. So your actual u is us plus ut. Only one of the components is 0. We have other components still pending to do, and which will be actually transient temperature distribution. Okay, t equal to 0 పెట్టాం కానీ 0 రాదు because ut is there. So k equal to 0 is the one which gives us only steady state temperature distribution, but nowhere related to time. Okay, we'll go for next case then. Case 2, which is k is positive plus lambda square. Therefore, x double dash minus lambda square x equal to 0 and t dash minus c square lambda square t equal to 0. Okay, this implies capital X is equal to A e power lambda x plus b e power minus lambda x and capital T equal to capital C e power c square lambda square t. C square lambda square t. Therefore, u of x comma t equal to, in fact, you know one thing, though I am trying to solve like this, but the boundary conditions nowhere related to t expression. Just exclusively boundary conditions only I can solve actually, without taking into consideration this. When I apply two boundary conditions, this is nowhere related actually. It's just related to this expression only, not to this expression. Okay, which in fact gives us US in that case. Anyway, this is nothing but a e power lambda x plus b e power minus lambda x into c e power c square lambda square t. This directly we can say that cannot be accepted. Why? Time constraint, if you see, as t goes to infinity, c square lambda square both are positive. As t increases, temperature increases here. As t increases, temperature increases cannot happen unless otherwise you have some heat source inside the body. Obviously, right? Unless you have an additional heat source inside the body, you cannot have increase in temperature as T increases. Are you getting that? And there is no mention of any presence of heat sources, either external heat sources or internal heat sources. There is no mention in this problem, in this scenario. Okay? Therefore, this can never ever happen. This cannot be accepted by any means. Unless either I have minus here, you cannot accept. Okay? Anyway, that would be the next scenario anyway, which would be the transient conditions. But anyway, even if you want to prove also, we can prove by using boundary conditions, say that this is invalid case. Okay. Just try to apply. U of 0 comma t equal to a plus b into, or maybe c also you can put it inside, which becomes d plus e power c square lambda square t equal to 0, which implies d plus e equal to 0, which is equation number small a, and u of L comma t equal to d power lambda L plus e power minus lambda L into e power c square lambda square t, also given to be 0, which implies d power lambda L plus e power minus lambda L equal to 0, equation number B. Solving A and B, we get, what we get? D is 0, E is 0. Therefore, u of x comma t equal to 0 cannot be accepted as solution of heat equation 1. Because it does not even reflect steady state or even transient state. Both the states it could not reflect, therefore this cannot be accepted, and you can take a note after this. Note. What is the note? Observe that as T increases, temperature U is increasing. And as T goes to infinity, small t, goes to infinity, U goes to infinity. which cannot happen in a body unless there are heat sources inside the body, unless there are heat sources inside the body. This particular aspect is pretty clear for us, okay, because this something here itself, instead of doing all these things, if you want to cut short your answer, you can directly mention here saying that as t goes to infinity, u goes to infinity, which cannot be accepted as a solution of a heat equation. That's it. Okay, that can be done. Any questions here? Maya? Okay. Let k equal to minus lambda square. This implies x double dash plus lambda square x equal to 0 and t dash plus c square lambda square t equal to 0, which implies capital X equal to a cos lambda x plus b sin lambda x and capital T equal to capital C e power minus c square lambda square t. Therefore, u of x comma t equal to, we see d cos lambda x plus e sin lambda x into e power minus c square lambda square t. Okay, now let us apply boundary conditions. U of 0 comma t equal to, actually, you know, from here this expression in fact represents transient state. Case 1 represents steady state, case 3 represents transient state. Unless you add both of them, it will not be u of x comma t. So your actual u of x comma t will be equal to us of x, which is 0 in our case, plus ut of x comma t. That's what happens. Okay. So when I say u of x comma t is equal to us of x plus ut of x comma t. Okay. Just for our reference, I am telling you. Though anyway, we try to do, actually this is somewhere in the back of your mind, it works for you actually, it should work for you actually, this particular expression. In fact, since this is 0, of course, suppose if it is not 0 also, in the case of mx plus c case also, if you see this one, and the conditions are actually given on u, not on ut or not on us directly, okay. So if I apply those conditions, u of 0 comma t equal to us of 0 plus ut of 0 comma t. X equal to 0 case, okay. Now, suppose if us of x is equal to y equal to mx plus c, ax plus b or whatever case, okay, then I will put x equal to 0. From this expression, I will get conditions for ut of x 0 comma t equal to u of 0 comma t minus us of 0, okay. In fact, this in fact is ut actually, it's not just u. It is ut actually, okay. Therefore, u of x comma t would be us of x plus ut of x comma t. But since in this present case us is 0, whatever conditions on u are there, it becomes conditions on ut also. Are you getting? Suppose us is non-zero, then to solve this expression and get the values of d and e, you have to use conditions on ut only, not on u, if us is non-zero. How to get that, we will discuss later. Are you getting? Similarly, u of L comma t, if I consider, which is nothing but us of L plus ut of L comma t. Similarly, u of x comma 0 I will keep, us of x plus ut of x comma 0. So this three expressions gives ut conditions. What is ut? This is ut. So to get the values of d and e, you have to use these ut conditions. Ut conditions, not u conditions. U conditions are in a broader sense, bigger one, the whole one. But this case 3 gives only for ut. The solution of ut will be given by case 3. And in case 1 itself, I would have already got what is us. And this expression is something I am telling you which has to always work in your mind. This expression always holds good. Okay? This expression gives us everything. In textbooks, what happens is, every case they solve in different ways. But actually, it's not different ways. All of them are same. When they mention that case 1 is invalid, it means that steady state is 0 steady state. Only then it can be invalid case. Or else case 1 cannot be invalid. Okay? Fine. Anyway, I'll come back to this later. But in our present case, since us is 0, u and ut becomes the same. The conditions of u and the conditions of ut are one and the same in the case of this present case only. Since it's a simple case. Okay? Anyway. U of 0 comma t equal to cos 0 1 sin 0 0 e power minus c square lambda square t, which is given to be 0, which gives me d equal to 0. Next. U of L comma t is equal to d0 e sin lambda L into e power minus c square lambda square t, which also is given to be 0. Exponential cannot be 0, okay, unless otherwise t goes to infinity. But in our case, it's any time t, this has to happen. If e also is 0, then u becomes 0. But we have another case, sin lambda L can become equal to 0, okay. So we'll use the case where, because I'm trying to find the solution, always get those things which gives us the solution. This also implies lambda L equal to n pi, n running from 0, 1, 2, so and so. This gives me lambda equal to n pi by L again. Therefore, as in the case of wave equation, now u of x comma t becomes equal to sigma n running from 0 to infinity en sin n pi x by L into e power minus c square n square pi square t by L square. This is equation number 2, 3. Which in fact is my ut. Again, I have one more thing to find out. En also I have to find out. Okay? En also I have to find out. I have one more condition to find En. Time condition is there. Okay? To find what is my En, which in fact obviously gives us a Fourier series, and you know how to solve a Fourier series. Okay? Applying that last condition, u of x comma 0 equal to f of x, which is sigma n running from 0 to infinity En sin n pi x by L is a Fourier sine series. Is a Fourier sine series. Is a Fourier sine series. Therefore, En equal to 2 by L integral 0 to L f of x sin n pi x by L dx, which is equation number 4. Which is equation number 4. Therefore, the solution of the given heat equation is given by 3 and 4 together. Take a question. And again I am telling you, what you got here is UT. UT, okay? U is US plus UT. US is 0, therefore U equal to UT. I am telling it clearly again, okay? Because in the next level, if the temperature distribution is different, non-zeros, then you can clearly, explicitly see US will also be there. The case 1 plus case 3 will be the answer. US plus UT will be the answer. Okay? Take a question. Take a question. Determine the solution of dou u by dou t equal to c square dou square u by dou x square with the boundary conditions u of 0 comma t equal to 0, u of L comma t equal to 0 and u of x comma 0 equal to x. So quite obviously, when you apply, what you get is you directly land it here. Is it or not? Because 2, 0, 0 boundary conditions, you land up at somewhere here. Okay? And then f of x is given to be x. You can get En equal to put x here and get the answer. That's it. It's a very simple question. Can you give me the answer? What is En? Cos n pi lo ichi untundi minus 2l by n pi into cos n pi, and cos n pi is minus 1 whole power n. And substitute here directly in the place of En. Very simple question. Is that okay? Take one more question. Solve one dimension diffusion equation. Heat equation is also called as diffusion equation. Solve one dimension diffusion equation in the region 0 less than or equal to x less than or equal to pi, t greater than or equal to 0, subjected to, in the region 0 less than or equal to x less than or equal to pi, t greater than or equal to 0. That means the length of the rod is pi, L equal to pi. Okay. Subjected to, first, u remains finite as t tends to infinity. What does it mean? Enti? Steady state. U remains finite as t tends to infinite. Doesn't depend on x. Avuna. T to maatladutunte t goes to infinity, u has to remain finite. It happens only in the case of case 3, not case 2. Case 2 is directly invalid. That's what it's saying. మాకు ఆల్రెడీ తెలుసుగా కేస్ 2 ఇన్వాలిడ్ అంటే కదా. ఇది ఇన్ఫర్డ్ అనమాట. ఇన్ఫర్డ్ ఇన్ అవర్ అండర్స్టాండింగ్. As t goes to infinity, suppose u does not remain finite, means it has to go to infinity. T goes to infinity, u goes to infinity is not accepted, right? That means there are no heat sources inside. There are no heat sources inside. When the transient conditions prevail, then as t goes to infinity, u has to remain as a finite value. 0 is finite only, na? Okay. Or us of x would be there, which might be 0 or which might be some ax plus b, which might be finite always. Is it or not? Next. Okay, UPSC has a tendency of confusing us by giving certain additional statements which are already implied ones. మనమేమో ఇది సెపరేట్ గా స్పెషల్ గా ఇచ్చాడు అనుకుంటాం. u equal to 0 if x equal to 0 and x equal to pi for every t. What does it mean? Boundary conditions 0 and 0 boundary conditions. Okay. Third one, at t equal to 0, u equal to x, 0 less than or equal to x less than or equal to pi by 2 and equal to pi minus x, pi by 2 less than or equal to x less than or equal to pi. What it means? It means that while performing this integral 0 to pi, you have to split between 0 to pi by 2 and pi by 2 to pi. Okay? Chestara? Fatafat chesi cheppandi answer. So take this En. Of course, n also you can start even and odd. What happens to n? When n is even, what is the value? N is odd, what is the value? That also you can put it here actually. Okay? Because when n is even, 0, n is odd, then plus 1 or minus 1, depending upon n value. Right? Okay, that also you can, if you want to portray that one also you can do that. Okay. One more scenario, type 2 scenario. Type 2 scenario. If at all one of the phase is maintained at temperature u0, that means the conditions that you have is u of 0 comma t is 0, u of L comma t is maintained at u0, u of x comma 0, let it be some temperature distribution inside. Some temperature distribution inside f of x. Okay? So let us go to case 1. K equal to 0 case. K equal to 0 case. So u of x comma t comes out to be a, b, c, dx plus e. I am not writing every step now. Not writing every step, okay? U of x comma t equal to dx plus e. So in fact this gives us steady state temperature distribution, okay, not the complete temperature distribution. Though we write u of x comma t. U of 0 comma t is given to be 0 equal to e. U of L comma t is equal to u0, which is d into L. Therefore d equal to u0 by L. Therefore u of x comma t equal to u0 by L into x is the steady state temperature distribution. Let us of x is equal to u0 by L into x. Mx plus c, c is 0. Because one side you are maintaining 0. It means that a rod like this is 0, this is maintained at u0. That u0 tomorrow you will be given a value there. So you substitute the value, that's it. Okay. So case 2 anyway invalid. Okay. So don't just write invalid in the case of your exam, you just show that it cannot be a solution. Okay. Now directly go for case 3. K equal to minus lambda square. Therefore, u of x comma t is equal to a, b, c, d. D sin lambda x. D sin cos the first మన రాసేది మామూలుగా d cos lambda x plus e sin lambda x into e power minus c square lambda square t. Now write a statement. Observe that as t goes to infinity, don't write completely in English. As t goes to infinity means you write as t tends to infinity. You write like that. English lo రాయకండి t goes to infinity and GOESE. Okay. T goes to infinity, u tends to 0, which represents transient condition state. Transient condition state or transient state of the body. Transient state. Therefore ut of x comma t equal to d cos lambda x plus e sin lambda x into e power minus c square lambda square t. Clear? Clear? Okay. Don't get confused here. Case 1 steady state. Case 3 transient state. Add them, you will get temperature distribution u of x comma t always. Okay. That's how things should be. Right. Even the first problem also, somewhere in the back of our mind, this is what it is working. Though we made ut as u only because us is 0 in that case. Therefore, u of x comma t equal to us of x plus ut of x comma t. This implies u of x comma t equal to us of x u naught by L into x plus ut d cos lambda x plus e sin lambda x into e power minus c square lambda square t. This is the expression, equation number 1, 2, 3. Is okay na? us of x plus ut of x comma t. Now apply the conditions. U of 0 comma t equal to, these conditions are not for ut, these conditions are for u. Okay. Of course, boundary conditions, you might ask me, boundary conditions, why you use these things? Boundary conditions of u are nothing but boundary conditions of us only on x, right? This is 0 plus cos 0 1 sin 0 0 d e power minus c square lambda square t, which is given to be 0, which implies d equal to 0. Okay. Now u of L comma t is given to be u naught, which is equal to x is L, therefore this also is u naught plus d is 0 e sin lambda L into e power minus c square lambda square t, which gives me sin lambda L equal to 0. U naught cancels, sin lambda L equal to 0. This gives me lambda L equal to n pi, n running from 0, 1, 2, so and so. This gives me lambda equal to n pi by L. Okay. Therefore, u of x comma t equal to u naught by L into x plus sigma n running from 0 to infinity, substituting, okay, n running from 0 to infinity en sin n pi x by L into e power minus c square n square pi square t by L square. This is equation number 4. Okay, equation number 4. One last condition, this one, u of x comma 0 is given to be equal to f of x. This is equal to time t equal to 0 case, which is equal to u naught by L into x plus sigma n running from 0 to infinity, 0 to infinity en sin n pi x by L. F of x is also some function of x only, okay, is a Fourier sine series, is a Fourier sine series, is a Fourier sine series. Therefore, En equal to 2 by L integral 0 to L. What would be this one? F of x minus u naught by L into x sine n by x by L dx, which is your equation number 5. So 4 and 5 together gives solution. n equal to 0 పెట్టినప్పుడు 4 by ఇందాక వచ్చింది కదా 4 pi by n square అట్లా or 4 by pi n square అట్లా కదా. జీరో అప్పుడు పైన ఏమొస్తుంది sin n pi. ఎగ్జాంపుల్ చూద్దాం ఒకసారి. 0 by 0 వచ్చిందా, 4 by pi n square sin 0, 0 by 0 ఫామ్లోకి వస్తుంది. అప్పుడు పైన సైన్లు ఉన్నాయి, sin n పైలు ఉన్నాయి, 0 by 0 ఫామ్కి వస్తుంది, ఇండిటర్మినేట్ ఫామ్. ప్రాబ్లం లేదు, ఓకే. అంటే బేసికల్గా వై ఐఎమ్ టేకింగ్ దట్ n equal 0 ఆల్సో ఈజ్ బికాస్ ద ఫస్ట్ టర్మ్ ఈ నాట్ ఉంటుంది కదా, ఆ ఈ నాట్కి ఒక్కోసారి ఇంపార్టెన్స్ వస్తుంది. ఆ ఇంపార్టెన్స్, సమ్ ఆఫ్ ది ప్రాబ్లమ్స్ వీ హ్యావ్ దట్ ఇంపార్టెన్స్, ఇక్కడ పెద్ద అవసరం లేదు. ఓకే, దెన్ దట్ వర్క్స్ అవుట్. ఓకే, దట్స్ ద ఓన్లీ రీజన్. ఆర్ ఎల్స్ ఇఫ్ యూ లుక్ ఎట్ మై ప్రీవియస్ బ్యాచెస్, ఐ హ్యావ్ టేకెన్ n equal to 1 only. I started with n equal to 1 case only. Because somewhere I felt like why we should modify only in one that particular problem. Let us go with a common way, n equal to 0 to infinity all the way. Okay. So in the examination you will be given specific values of u naught, which is a constant, okay, and f of x also can be given. And one more thing is, instead of maintaining 0 here, sometimes they maintain 20, 100 or 2080, 2060, whatever. In which case, it's not just u naught L, u naught x by L, mx plus c also would be there in that case. Okay, so in the steady state, what is that steady state? Cx plus d, ex plus d, whatever. Take a question. సింపుల్ చేద్దామా కష్టమైంది చేద్దామా అని ఆలోచిస్తున్నా. ఓకే, సింపుల్ లేదు, కష్టం లేదు, డైరెక్ట్ చేసి పడేద్దాం. చిన్న చిన్న చేస్తే వేస్ట్. Okay, now there's nothing like difficult or easy question here. All questions concept is same. Okay. Now some people say some difficult questions. The difficulty is just based on one simple thing, that this f of x, to find f of x they will give some conditions to us. Instead of they giving what is f of x, we have to find f of x. How to find f of x? What they do is a rod outside somewhere, okay? It already has got some temperature distribution. What kind of temperature distribution for that rod? It is a steady state distribution already exists in that. Steady state is there. What is that steady state? They maintain 0 here, 100 here for a length L. 0, 100 for a length L, they are already maintaining some temperature distribution inside. That we can easily find. It would be 100 by L into X. 100 by L into X would be the temperature distribution in that one. Okay. Suppose they are maintaining 20 and 60, like earlier I have given. They are already maintaining 20 and 60, which is outside. 20 and 60. So it would be 20 plus 4x. 10 distance is length, or okay, 40 by L into X. Okay. That is already being maintained. So there is a temperature distribution which is already f of x. Okay. That is suddenly brought here, and now I maintain different temperature distributions here. Are you getting? That different temperature distributions would be these things. Then f of x is already given to us in terms of an already existing steady state temperature distribution. Are you getting? So when that already existing temperature distribution, which is steady state temperature distribution, is brought inside, and with new boundary conditions, and the initial condition being or whatever already is there, that means this is given, and this also we found out. For this, later on as t goes to infinity, a new steady state condition will come, which I will obtain through case 1. Are you getting? And then case 3, which would be the transient condition state based on new conditions that are given to us. That's the only thing. That's the toughness of the question. Okay? Now go with the question. The ends, capital A and capital B, the ends, E-N-D-S, ends, capital A and capital B of a rod of 10 centimeters in length, 10 centimeters in length, is kept at 0 degree centigrade and 100 degree centigrade, is kept at 0 degree centigrade and 100 degree centigrade until the steady state conditions prevail. Until the steady state conditions prevail. Suddenly, continue it. Suddenly, the temperature at the end A is increased to 20 degrees and the end B decreased to 60 degrees. Now suddenly I started maintaining 20 and 60 now. Earlier it was 0 and 100. Suddenly 20 and 60 I started maintaining. Okay. Find the temperature distribution in the rod at any time t. At any time t. Understood? Understood the question? So, what we'll do is, first thing, prior to changes in temperature. Okay, prior to changes in temperature, u of x or u of 0, let u of x be equal to ax plus b. Since nothing is given, it's a homogeneous body only. So since a steady state temperature distribution is maintained already, obviously it will be linear straight line temperature distribution of y equal to mx plus c. Okay, so ax plus b. U of 0 is given to be equal to 0 and u of 10 is given to be equal to 100. Okay, therefore u of 0 equal to b equal to 0, u of 10 equal to 100 equal to a into 10, which gives me a equal to 10. 100 by L into x actually. 100 by L is the slope. Okay, 100 by 10. 10 and 10, 100. Okay. Therefore, u of x equal to 10x is the steady state temperature distribution. Okay. Next, after changes in temperature. After changes in temperatures, u of 0 comma t equal to what? 20. U of 10 comma t equal to 60. U of x comma 0 equal to 10x. Here you can write is the steady state temperature distribution prior to changes. Is that okay? Is the steady state temperature distribution prior to changes becomes my initial temperature distribution for the new scenario. Is that okay? Previous whatever is steady state temperature distribution now becomes initial temperature distribution for the new temperature distribution scenario, new boundary conditions scenario. Is that clear? Okay. Now, let the solution of the differential equation be u of x comma t equal to x into blah 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 blah. Case 1. Okay, case 1. Case 1, k equal to 0, which gives me u of x comma t equal to abc dx plus e. Dx plus e. Okay. With the new scenario, here I have just taken ax plus b and tried out. Okay. In fact, this also is case 1 only, but I don't want to go with case 1 and all those stuff. It's just steady state reached already. Therefore, only u of x comma t is us of x only. Ut has already become 0 for this. Okay, fine. Now this is this one. Now u of 0 comma t is 20, which is equal to e. U of 10 comma t equal to 10d equal to 60. Therefore, d equal to 6. Adenti? Antena? Plus 20 only, 10d plus 20. E is 20 plus 20 equal to, therefore this is equal to 4. Therefore, u of x comma t equal to 4x plus 20 is the steady state temperature distribution, okay, Therefore, us of x, or maybe let us of x equal to 4x plus 20. You understand it? I am going in a very phased wise manner. Okay. Finally, coming back to the same old story. Case 2, k equal to plus lambda square, invalid. Case 3, k equal to minus lambda square, which gives me u of x comma t equal to a, b, c, d. d cos lambda x plus e sin lambda x into e power minus c square lambda square t. Again we will write, observe that as t goes to infinity, u goes to 0. Therefore, it is a transient temperature distribution. Therefore, ut equal to this one. Therefore, u of x comma t equal to us of x plus ut of x comma t. This implies u of x comma t equal to 4x plus 20 plus d cos lambda x plus e sin lambda x into e power minus c square lambda square t. Now apply the conditions. U of 0 comma t equal to 20 equal to 20 plus cos 0 1 sin 0 0 d power minus c square lambda square t, which gives me d equal to 0. Next, u of 10 comma t equal to 60 equal to 60 plus e sin 10 lambda into e power minus c square lambda square t, which gives me sin 10 lambda equal to 0, 10 lambda equal to n pi, n equal to 0, 1, 2, so and so, gives me lambda equal to n pi by 10. Therefore, u of x comma t equal to 4x plus 20 plus sigma n running from 0 to infinity en sin n pi x by 10 into e power minus c square n square pi square t by 100. Equation number 3, okay, 3 or 4, whatever. Okay, Nanta? Same, ditto, everything same, no change anywhere. U of into the x comma 0 is given to me on each other 10x, 10x is equal to 4x plus 20 plus sigma n running from 0 to infinity en sin n pi x by 10 is a Fourier sine series. Therefore, en equal to చెప్పండి 2 by L, L అంటే 10 మళ్ళా, ఓకే 2 by 10 ఇంటిగ్రల్ running from 0 to 10, 0 to L కదా, ఇంటిగ్రల్ 0 to L, 10 minus this thing, which is 6x minus 20 sin n pi x by 10 dx, which is equation number, equation చేయాలి కదా. But anyway, you try to solve it and give me answer. So that En comes out to be minus 1 by 5 into 400 by n pi into minus 1 whole 4 n plus 200 by n pi. అంటే minus 1 whole 4 అంటే cos n pi అది వచ్చి ఉంటుంది అక్కడ అంతేనా. ఓకేనా. Take one more question for your homework. Though I was cut shorting my answers when it comes to solving, but in the proof I have given you everything, all the steps, every step I have given you. In the final examination, depending upon the marks, suppose it is given only for 10 markers, suppose, assuming that. Of course, heat equation they don't give for 10 marker by any means, but suppose wave equation is given for 10 markers. So you directly mention case 1 k equal to 0, case 2 k equal to plus lambda square, all are invalid because wave equation is a periodic function. Periodic function comes only with k equal to minus lambda square. So directly go to case 3 and jump into that. That depends upon the marks awarded to a given question. So you should be very smart. Remember, at the same time, the amount of space that is provided also depends upon the marks awarded to that question. So accordingly, you have to manage your answer also, the length of the answer. Okay. So always open the other pages also and see how much space is available for a given question. So just don't keep on solving them. See amount of space available and then plan accordingly. One question for your homework. This question has 2 sub questions. Take it. A insulated rod of length L, a insulated rod of length L has its ends, ENDS, capital A and capital B maintained at 0 degree centigrade and 100 degree centigrade respectively, 0 and 100 degree centigrade respectively, until steady state conditions prevail. Until steady state conditions prevail. Okay. B, the end B, capital B, is suddenly reduced to 0 degree centigrade and maintained at 0 degree centigrade. Find U of x comma t. The end B is suddenly reduced to 0 degree centigrade and maintained at 0 degrees. Find U of x comma t. What happened? Initially, it has got some temperature distribution which would be 100x by L. 100x by L. Now, suddenly the other 100 also started maintaining at 0 degrees, which gives us 0 steady state. The case 1, which is valid case, which gives me 0 now. Us of x becomes 0. So what remains is ut of x comma t, which exactly becomes equal to u of x comma t only. Is that okay? Okay. Further, the question is continued now. Find also the temperature distribution if the change consists of raising the temperature of A to 20 degrees, and reducing that of B to 80 degrees. Okay. So again 100x by L becomes your initial temperature distribution, and u of 0 comma t is 20, u of L comma t is 80. That's it. Okay, and regularly use only. So note the answers. For the first one, the answer is u of x comma t is 200 by pi sigma minus 1 whole power n plus 1 by n sin n pi x by L e power minus c square n square pi square t by L square. For the second one, the answer is u of x comma t equal to 20 plus 60 by L into x, this is US, minus 40 by pi into sigma m running from 1 to infinity, m in the majula, sin 2m pi x by L to e power minus 4 c square m square pi square t by L square. అంటే n లో ఉంటుంది, ఈవెన్ ఆర్ ఆడ్ అయినప్పుడు one of them becomes 0, other becomes కదా, ఈవెన్ అన్నప్పుడు 2m అవుతుంది, n equal to 2m కదా. ఓకే, అంటే ఆల్రెడీ అది కూడా టేకెన్ కేర్ ఆఫ్. One last variety, it's all about heat fluxes and insulations. Suppose I have a rod, okay, suppose this is x equal to 0 end, this is x equal to L end. This is the boundary of the rod, boundary, okay. We have external environment here and this is inside, okay. Suppose if I give some heat source is always supplied through heat flux, which will always be a constant heat flux Q naught. A constant heat flux Q naught is maintained at the end x equal to L. It means that there is some exchange of heat between both the surroundings, both the bodies, body and the external body, okay, along x direction. Is it or not? It's along x direction only I am supplying heat flux. That heat flux is always represented as dou u by dou x, because it is the gradient along x axis. Suppose I am supplying like this heat flux, then it should have been dou u by dou y. Are you getting? And this, that too, this is at what point? X equal to L point. At x equal to L, dou u by dou x equal to Q naught. Dou u by dou x equal to Q naught. This is a constant heat flux is maintained at x equal to L. Then the condition that I am going to take is dou u by dou x at x equal to L equal to Q naught. Similarly, suppose if I insulate, insulation means there is the exchange of heat between the body and the surroundings is 0 along x direction. That means dou u by dou x at x equal to 0 is 0. Are you getting that? So when insulation is there, it means that insulation along x direction only. The exchange of heat between the two bodies along x direction is not there, is 0, is not present, means that dou u by dou x at x equal to 0 and is equal to 0. If I maintain constant heat flux at one of the ends x equal to L suppose, then dou u by dou x at x equal to L equal to Q naught. Take a note. if heat supplied at the end x equal to L, if heat supplied at the end x equal to L such that constant flux Q naught flows FLOWS at x equal to L, then dou U by dou X at x equal to L equal to Q naught. Sometimes we also write it as L comma T. Dou U by dou X, L comma T equal to Q naught. Both are same. At any time T, that constant heat flux keeps on flowing at any time T. Okay? Fine. Now, if one of the ends x equal to 0 is insulated, if one of the ends x equal to 0 is insulated, then dou U by dou X at x equal to 0 equal to 0. Now, in all these scenarios, what happens is, if you look at the conditions, one of the conditions, suppose some temperature is maintained, suppose here temperature is maintained, here flux is there, or here insulated, something like that. When insulation is there, for this condition, you will go with dou U by dou X, right? When you go with dou U by dou X, what happens? You will get sin lambda x differentiated, therefore cos lambdas you will get. So when cos lambda L becomes equal to 0, cos lambdas become equal to zeros, then lambda will be odd multiples of pi by 2. Odd multiples of pi by 2s. Ante kada? 90 degrees and other one is, okay. So odd multiples of pi by 2n plus 1 into pi by 2 is then. Are you getting? So it's not like just minus c square, n square, pi square t. It will be minus c square, 2n plus 1 whole square, pi square, t by L square, all those things. Okay, are you getting? Okay. So whenever heat flux or insulation comes, you can actually verify that also. So obviously, differentiation would be there. Instead of sin lambdas becoming equal to lambda L becoming equal, cos lambda L become equal to 0 in that case. Of course, that also depends. We'll see that. Take a question. A uniform rod of length L. A uniform rod of length L whose surface is thermally insulated. Whose surface is thermally insulated is initially at a temperature U naught, is initially at a temperature U naught at time t equal to 0. At time t equal to 0. Continue the question. One end is suddenly cooled to 0 degrees, 0 degrees and subsequently maintained at this temperature, and subsequently maintained at this temperature. Continue. The other end remains thermally insulated. The other end remains thermally insulated. Find the temperature distribution inside. Find the temperature distribution inside. Okay. So what it says is, actually the entire body is thermally insulated. The whatever I got a body which is completely all sides thermally insulated. Okay. When it was insulated, already there exists a temperature distribution inside, which is a constant temperature distribution of U naught. Okay. That means U of x comma 0 is U naught. Is that okay? What happened? Suddenly one of the ends is, in fact earlier it was insulated both sides. In fact this also is already insulated along y and z also, it is already insulated one basically. Okay. Every side it is. Suddenly what happened? One of the ends started maintaining at 0 degrees. The other end remains insulated. One end 0, other end remains insulated. So it means U of 0 comma t is 0, dou u by dou x at L comma t is 0. అట్లా కూడా చేసుకోవచ్చు. The other way round also. This is L, this is 0. That means this is insulated, the other end is maintained at 0. You can also do that. I think no, two answers will be there. ఒక దాంట్లో ఒకటి L minus x పెట్టుకుంటే వస్తుంది ఆన్సర్. అంతే కదా? Anything you can do. ఇది 0, ఇది L. రైట్? చేస్తారా? చేయండి. మీరు చేయండి, నేను చేస్తాను. ఎవరు ఫాస్ట్ చేస్తారో చూద్దాం. సరే, మీకు ఇనీషియల్ లీడ్ ఇస్తాను. మీరు కొద్దిసేపు చేసిన తర్వాత నేను స్టార్ట్ చేస్తాను. చిన్నప్పుడు సైకిల్ పోటీలు పెట్టుకున్నప్పుడు కేస్ 1 ఏమొచ్చింది చెప్పగలరు ఎవరన్నా? నేను అప్పుడే కేస్ 3కి వచ్చేసాను. ఓకేనా? ఇది స్టడీ స్టేట్ టెంపరేచర్ డిస్ట్రిబ్యూషన్ 0. ఎందుకు? వై? See, the other side is insulated. There is no heat source for this one. Whatever heat is there inside, and since I am maintaining 0 here, whatever heat is there inside, it slowly dissipates. It slowly dissipates because of transient property. Finally, it has to come to 0 only. So, steady state finally becomes 0 here. Okay? So, u of x comma t equal to 0 ut of x comma t, which will be equal to ABC d cos lambda x plus e sin lambda x into e power minus c square lambda square t. మీరు చేసుకోండి. u of 0 comma t equal to 0 sin 0 0 cos 0 1 d dou u by dou x equal to e lambda cos lambda x into e power minus c square lambda square t dou u by dou x at L comma t is given
to 0. So cos lambda x lambda L lambda L equal to 2n plus 1 into pi by 2 and then 0 1 to 7. So this is lambda equal to 2n plus 1 into pi by 2l. Therefore, u of x comma t equal to sigma L from 0 to infinity En sin lambda x 2n plus 1 into pi x by 2l minus c square whole square pi square t pi 4l square. Equation number 3 u of x comma 0 is equal to sigma L from 0 to infinity En sin 2n plus 1 into x by 2l is here. So here sin space so L equal to 2πL into the
A conducting bar of uniform cross section, a conducting bar of uniform cross section lies along x-axis, with ends at x equal to 0 and x equal to L. With ends at x equal to 0 and x equal to L. It is kept initially at temperature 0 degrees and its lateral surface is insulated. There are no heat sources in the bar. Next. The end x equal to 0 is kept at 0 degrees. And heat is suddenly applied at the end x equal to L. So that there is a constant flux Q naught. At x equal to L. Find the temperature distribution in the bar for T greater than or equal to 0. 30 greater than or equal to 0. So left hand side 0, right hand side constant heat flux Q naught. Initial temperature distribution. What is initial temperature distribution? 0. So the question gives something like this: u of 0 comma t equal to 0, dou u by dou x at L comma t equal to q naught, u of x comma 0 equal to 0. ఓకేనా? ఇంటికెళ్ళి చేసుకుంటారా? ఇప్పుడే చేస్తారా? ఏంటి ఇప్పుడు చేస్తారా ఇంటికి వెళ్తారా? సరే చేయండి, ఫటాఫట్ చేయండి ఫాస్ట్. కేస్ 1, కేస్ 3. Steady state is Q naught x, huh? Okay. Answer. So u of x comma t equal to Q naught x plus sigma minus 1 whole power n plus 1 by 2n plus 1 whole square 8 Q naught L by pi square. Find 2n plus 1 into pi by 2l x e power minus 2n plus 1 whole square pi square c square t by 4l square. Epatya? Take this question. Find the solution of one-dimension diffusion equation satisfying. Find the solution of one-dimension diffusion equation satisfying. First one, u of x comma t is finite as t tends to infinity to dou u by dou x at x equal to 0 for every t, dou u by dou x at x equal to a is 0 for every t. Fourth, u of x comma 0 is equal to x into a minus x, 0 less than x less than a. Answer, u of x comma t equal to a square by 6 plus 2a square by pi square now. Here in this question there is a problem. Then in cheppina oka scenario vastundi. Because of these two, look at this is insulation at both the ends. When insulation is at both the ends, when you talk about US of x, which is ax plus b, dou u by dou x equal to a, which is 0, either x equal to 0 or x equal to a. X equal to 0 or x equal to both the ends, a is 0. So what remains is US of x comes out to be b actually. So your u of x comma t will be b plus ut, some sigma whatever it comes. Here maybe some en might be there. Are you getting? Itena? Kada? So u of x comma t is b plus, because the steady state condition comes out to be constant now. Some b. What is that b? I don't know. We also have to find basically. And en also is there. Okay. Now, when you apply u of these two conditions, you will apply and you will get this sigma everything, whatever. When you apply this one, u of x comma 0, which is x into a minus x is equal to b plus sigma en e power minus something. Right? En sin ఉంటుంది కదా, sin whatever, obviously 2n plus 1 into pi x by 2l whatever. So here also en sin 2n plus 1 e power minus of something. T equal to 0, therefore this will not be there. So this would be 2n plus 1 into pi x by 2l whatever. There are two things you have to find here, not just en. There are two things, because this is also is unknown. This is not a given constant. B is not a given constant. Earlier it was a given constant, because a steady state condition came out to be some u naught or something, a constant we got. Okay, but now it is not a constant. This is also is an arbitrary constant now, which you have to find out. Okay, so for this one, anyway you are going to multiply throughout with sin 2n plus 1. Sin వస్తుందా cos వస్తుందా? Cos వస్తుంది యాక్చువల్గా, బికాస్ డిఫరెన్షియేట్ చేసినప్పుడు అది పోయి cos వస్తుంది. ఇక్కడ cos వాట్ ఎవర్, cos ఏమొస్తుందంటే cos sin 0 అవుతుంది మళ్ళీ. సో cos n పై x by l వస్తుంది. n పై x పై a వస్తుంది. నేను లెంగ్త్ a ఇచ్చినట్టున్నాడు కదా, లెంగ్త్ a ఇచ్చాడు. ఓకే, n పై x by a you will get. Okay, now what happens, you will multiply throughout with cos n pi x, m pi x by a, in which case when I multiplied x into a minus x cos m pi x by a and integrate 0 to a is equal to b cos m pi x by a dx integrate from 0 to a plus sigma en cos n pi x by a cos m pi x by a dx integrating from 0 to a. This becomes 0. Okay, and this is possible when n equal to m, finite value, or else non-zero value. Rest of all of them are zeros. Therefore en would be equal to 2 by a integral 0 to a x into a minus x into cos n pi x by a dx. That will be en only. Next, from here multiplying throughout with, or not multiplying, just integrate from 0 to a, just direct integration, which gives me integral 0 to a x into a minus x dx is equal to integral 0 to a b dx plus integral 0 to a sigma en cos n pi x by a dx. This becomes 0 now. Therefore this is b into a. Therefore b equal to 1 by a integral 0 to a x into a minus x dx. So that's how you need to get b. This is a regular one. En is a regular one, Fourier sine series or Fourier cosine series. This is a regular one, Fourier cosine series. Okay, but this is the one directly integrate from 0 to a. This anyway becomes equal to 0. Okay, when this becomes 0, b you got it, and here en you got it. That's all it had. Okay, now this is what which I was explaining earlier, yesterday's class in the beginning. When Fourier sine series comes or Fourier cosine series comes, why en becomes like this? But you should know how it comes like this also. Number one. Number two, whenever there is something is there, some arbitrary constant is there, how to get the value of that arbitrary constant is something which I was talking about yesterday. Okay, fine. So the final answer is, so when I compute this one, I get a squared by 6. That b comes out to be a squared by 6 plus rest of that. The rest of that is 2a squared by pi square sigma pi square, n square also comes inside. So minus 1 whole for n plus 1 minus 1 by n square into cos n pi x by a into e power minus n square pi square c square t by a square. Okay na? సరే ఎక్కడో కొన్ని తగులుతూ ఉంటాయి ఇట్లా. సో this steady state distribution coming out to be an arbitrary constant is something which is new phenomena. We were not able to anticipate that. Okay, now this is what it happens. How to find this arbitrary constant value which cannot be found out by other means. Okay, one single condition itself has given that avenue for us now. Okay. Take one more question, last one. Obtain the temperature distribution y of x comma t. Obtain the temperature distribution y of x comma t in a uniform bar of unit length. In a uniform bar of unit length, whose one end is kept at 10 degrees centigrade and other end is insulated, and y of x comma 0 equal to 1 minus x, 0 less than x less than 1. The answer here is y of x comma t equal to 10 plus sigma bn minus 1 whole power n 8 by pi square. 2n minus 1 రాశాను, సరదాగా రాసుంటాను. 36 by 2n minus 1 into pi సరదాగా అంటే 2n plus 1 బదులు 2n minus 1 రాశా అంతే. sin 2n minus 1 into n కాదు, ఇదే n కాదు, pi x by 2 into e power minus of 2n minus 1 whole square into pi square c square t by 4. Okay, fine. That's the end of heat equation.